For the first question, they're asking for what can an ampere be expressed as. So, if we're looking at our equation sheet, if we look to the Unit 2 side of it, down to current, you've got the equation for current over here, which is just I is equal to change in Q divided by change in T. So I is equal to change in Q over change in T, which is going to be coulombs for charge and seconds for time. So that gives us coulomb per second. So that gives us A as the answer to question 1. So for question 2, they're after the change in wave characteristics from ultraviolet to infrared in the electromagnetic spectrum. First thing to notice, electromagnetic spectrum speed is the same for all electromagnetic waves, so instantly we get rid of A and C from that. Next thing to do is to list out the electromagnetic spectrum, as we have over here. Remember my instructions, visible under X-ray glasses. Low frequency end is the radio waves, high frequency gamma rays. So it's decreasing frequency as we go this way from ultraviolet to infrared, so therefore it must be B. For question number 3, we've got the idea of efficiency for electrical motor. We've got electrical power coming in, mechanical power coming out. So what that means is we need the equation for efficiency. From our equation sheet, power output divided by power input. Remember the times by 100 is just to make it into a percentage. So power output in this, this is the power loss, so we don't really want this. We want the power output, PO, power input, PI. So we want PO over PI, which is D. Okay, so question number 4. One of the equations we're not given is involved in this question, so make sure you know the equation that is used in this situation. Talking about light going into a glass block, it's monochromatic, just means one colour, and thereafter a refractive index. So the first thing to think about when you think about refractive index is that's 1 over sine C, critical angle. So the critical angle is the angle at which total internal reflection takes place. You can see that's happening in this glass block, but the angle they've measured is incorrect. If they've measured it from the edge of the glass block, we need to measure it from the normal. So you draw your normal in, measure the angle. Well, you don't need to use a protractor. What you actually know is that's 90 degrees from here to here. If that's 55, that must be 35 to make it the full 90. So you do sine, 1 over of sine 35, which ends up being 1.74. So that's D. So remember, refractive index is 1 over sine C. Okay, so the next question, question 5, is talking about an electron that's been accelerated from rest through a potential difference of 5 kilovolts. So we know that is 5 times 10 to the 3 volts. Remember, kilo is times 10 to the 3. So they want the kinetic energy. Now, we've learned in the photoelectric effect that if you apply a voltage across a charged particle, you can give it energy. So we know that the electron volt is a unit of energy. So electron volts in this situation would be equal to half mv squared. Okay, because of the fact the electron voltage that's applied would become kinetic energy in this situation. Now this isn't an equation you need to know. The key thing you need to know is that the energy has been supplied by the potential difference and it's being applied to an electron. So the key idea is a charge of an electron that we have over here and the voltage that we have over here. So this part actually isn't even required. That is just the principle that's in play here. More on this will come in A2 Edexcel Physics. So the idea is we need to times the charge of an electron by 5 times 10 to the 8, so that's 1.6 times 10 to the minus 19 coulombs, which is charge of an electron. You forget that. It is there in the data sheet, so it is minus, but in terms of this, because we're calculating energy as a magnitude, we don't actually need the sign. And you multiply that by 5 times 10 to the 3 volts. Okay, so if we put that through our calculator, 1.6 EXP is the button that on the older calculators do times 10 to the quite quickly, minus 9 times by 5 times 10 to the 3, which gives us 8 times 10 to the minus 16, which is A. To the minus 16 joules. Moving straight on from question 5 to question 6, we've got a question where we've got a wave. So in this, they're investigating a wave using a microphone. They've got an oscilloscope screen. Now, normally, whenever you see an oscilloscope screen, they will give you some point in the question some information on the scale of the oscilloscope. So right now, there's no information on the actual oscilloscope screen itself, so it must be within the question. So we carry on reading. So the screen of the oscilloscope has a grid on it, and the x-axis, one division is 5 milliseconds. There we go. There's the information we're after. Milliseconds. Milli is times 10 to the minus 3, so that means, excuse me, that each box over here is 5 times 10 to the minus 3 seconds. They want to know the frequency. Well, we know that frequency is 1 divided by the time period. Again, it is not an expression that's given to you on the equation sheet. It's one of the facts you need to know. So frequency is 1 divided by the time period. So let's figure out our time period. The time period is the time for one complete wave. So if we start over here and go up, back down, and return to where we started in the same direction. So we're originally going up, so therefore it must end on the way up. So it's 4 boxes wide. 1, 2, 3, 4. 4 boxes, with each box being worth 5 times 10 to the minus 3. So 4 multiplied by 5 times 10 to the minus 3. Seconds for each box, so that gives us 20 times 10 to the minus 3 seconds is our time period, also 20 milliseconds you could write that as. Well, frequency is 1 divided by this time period, so frequency is 1 divided by 20 times 10 to the minus 3, so we put that into our calculator. 1 divided by 20 exp minus 3. So that gives us 50 as our answer there. Now this is frequency. We know the units of frequency is hertz. Let's check that. And there we are. Okay, note they've got answers that you would get if you put in 20 instead of 20 times 10 to the minus 3. So do be careful of the milliseconds. Okay, so question 7, automatically it's going to be asking about phase difference. You can see that from the sort of things I've got over here, and remember phase difference is linked to path difference. So it talks about waves emitted at a specific wavelength that are coherent, and they'll meet at a certain point, having travelled slightly different distances, straight away path difference. These waves now have a phase difference of 180 degrees, pi radians, which you also know is lambda over 2 in terms of a difference in a cycle. Which of the following could be the path difference? So there we go, path difference at this point. Well, if it's 180 degrees or pi radians, it must be lambda over 2. So I've listed next to it what all the other ones are in terms of how many degrees and how many radians. So I'll zoom in slightly so you can see those. So there we go, there's slightly blurry. Let's try and get a bit. There we go, that's better. Okay, so you can see the other 4 there as well. Number 3, sorry, there as well. Okay, so our next question over here has got a circuit. It's talking about a combination of resistors. As soon as combination of resistors is mentioned, you need to remember that series, resistors in series, they add up. So if you're 2 resistors in series, they literally add up. So if you have a 2 ohm next to a 2 ohm, that's 4 ohms all together. And if you've got them in parallel, remember it's a 1/over relationship. Okay, and they're connected to a 12 volt supply. There's negligible internal resistance. So there's no internal resistance in here to add to the situation. So looking at the circuit, you've got a parallel combination of resistors in series with a single resistor, and they're after the potential difference between A and B. So they're after the potential difference here. So in other words, they're looking at a voltmeter across here, and what would the reading on that voltmeter be? So first we need to sort of disassemble or combine this parallel combination we have over here, and we know from the equation sheet that resistors in parallel is a 1/R is equal to 1/R1 add 1/R2 add 1/R3. So we've got 2 resistors over here, so 1/R is equal to 1/R1 add 1/R2. So if you sub in our values for that, that's a 1/R is equal to 1/6000 because it's 6 kilo ohms, add 1/6000, which therefore gives us 2/6000 for a 1/R, which is the same as 1/3000, just simplifying the fraction. Therefore R must be equal to R must be equal to 3000, because if 1 over R is 1 over 3000, then R must be 3000. So it's 3000 ohms, or 3 kilo ohms. So this circuit can now be changed. So this can be got rid of, and you can replace this 6 kilo ohm resistor with one single 3 kilo ohm resistor here. So the two 6 ohm resistors are replaced instead by one single 3 kilo ohm resistor. That's the same idea. So these are in series, so the total resistance of this circuit ends up being 9 kilo ohms, and we know that 9 kilo ohms is somehow sharing 12 volts. So I want to figure out what is my relationship between 1 kilo ohm or 1000 ohms and 12 volts. So for every 12 volts for every ohm there is, how much of my 12 volts do I get? So I need to divide 12 volts by 9 kilo ohms, which gives me the nice value of 1.3 reoccurring. So some people would approach this by ratios and just see what it is by ratio, in the sense that that's 9 to 12, and therefore be able to figure out the voltage from that. This is a nice way of doing it, because it allows you to figure out for 1 kilo ohm I would get 1.333 reoccurring volts. So I'm after my 6 kilo ohm resistor, so I need to multiply this now by 6, and that would tell me what voltage I'd get out of this. Okay, and that gives me 8, therefore it's 8 volts. The next question is about Doppler shift. Now we're fully aware that Doppler shift is to do with objects of where there's relative motion, and that leading to an observable change in frequency or wavelength. So it says ultrasound is used to investigate the blood and artery in the human body by detecting a Doppler shift. The Doppler shift is used to measure the so the idea is a change in velocity, and that leads to a change in frequency or a change in wavelength. So we're looking for frequency, wavelength, or velocity. So diameter of the artery, not much way that Doppler shift allows us to do that. Size of the particles in the blood, again, not much way it could do that. Temperature, no, but velocity, definitely yes. So next question is about the effect of diffraction. Is more noticeable in everyday life than with sound, with sound rather than with light. Okay, so remember diffraction, the size of the wavelength has to be close to the size of the gap for diffraction takes place. So wavelength needs to be close to the size of the gap for diffraction to take place. So we're talking about with sound, we know it has a much larger wavelength compared to light, which is a small wavelength. Due to its high frequency. So let's have a look. So it's more noticeable in everyday life because sound is a much longer wavelength than light. It looks like that's the right answer. Let's just double check the rest of these. Sound is longitudinal. Longitudinal has got nothing to do with whether something is diffract or not. We know that both waves can diffract. Again, talking about one being mechanical and the other being electromagnetic, nothing to do with whether it will diffract or not. And sound travels more slowly through air than light does. Remember, speed has got nothing to do with diffraction. Not with a wave anyway. It does with a particle, but speed has got nothing to do with diffraction with a wave. It's all about whether the wavelength matches the gap, and therefore sound has a much longer wavelength than light is correct. Okay, moving on to question 11. So, question 11 shows a picture that we've seen before in class, where you've got electrons that have diffracted. So this is an experiment that we've done. We used an EHT around the back of the room that produced 5,000 volts that allowed us to accelerate electrons to hit a sheet of a crystalline material, and then hit a screen that allowed us to investigate what happens as electrons diffract. Okay, so it says in the question that the diagram shows a beam of electrons being fired towards a thin sheet, and the screens detect the electrons after they pass through the sheet. Okay, so the photograph shows a position of electrons as they strike the screen. So you can see there's the dark rings, there's maxima and minima, showing that diffraction has taken place there. So explain what can be deduced about the behaviour of electrons from the formation of this pattern. Okay, the first thing that you must state very clearly is this shows that diffraction is taking place. In no way through any of this have they mentioned diffraction at all. We know that this is evidence of electrons diffracting. So first thing that would state on here is electrons are diffracting. First key point to mention. It's a 3-mark question, so we need at least 3 points in this that are clear. So we've got to think about the conditions for diffractions to take place. So remember, for the condition for diffraction to take place is that the wavelength of the electron has to be similar to the size of the atomic spacing, or atomic size itself. So electrons have a wavelength similar to atomic spacing or atomic size. The final point is the fact that for this to be occurring, there must be electrons exhibiting wave-like behaviour. So we need to state very clearly here that electrons are behaving as a wave. Okay, so you might want to state that one earlier in terms of logic, but in terms of 3 points that will get you the marks, those are the 3 points. So question 12 is a very straightforward question, asking about a thermistor with a negative temperature coefficient. Okay, so that means as the temperature increases, the resistance decreases. So you can draw a line like that. Remember that's opposite to PTC, which is positive temperature coefficient. It would curve upwards. Normal wires of a PTC, normal wires of a positive temperature coefficient. As temperature increases, more lattice vibrations, more resistance. But remember, semiconductor materials, such as the ones that thermistors are made from, have this property because of the fact that as the temperature increases, more charge carriers are released. Which probably will tie into this question. With reference to the equation I equals N QVA, explain what percent of resistance of the thermistor as its temperature increases. So as the temperature increases, N will increase. Okay, so there we go, more charge carriers being released, which causes R to decrease, so less resistance, straightforward. As N increases, I increases, and this relates to R equals V over I, which is related to the second or third mark. Again, you've got this idea that there's more charge carriers, larger current, therefore you're proving that resistance must decrease, because if I is bigger, then R is smaller. And so as I increases, R must be smaller. There's your third mark. You could also say the drift velocity slightly decreases because if the temperature increases, more lattice vibrations, therefore more likely that there's going to be a collision, and therefore the drift velocity of the electrons will be less. Also, so that's another way of getting the third mark. Also, another way of getting the third mark is saying that A and Q are constant. Cross-sectional area is constant on this wire. You're not changing that. Neither are you changing the charge of an electron. So, next question has got a nice graph on there, which straight away you should identify as a graph of a diode. Straight away put a second symbol there just to remind you. Okay, so remember with the second symbol, arrow going this way only allows current to flow in one direction, that way around. So straight away, first question, diode. State the name of the component, diode. State the resistance of the component when the potential difference is 0.7 volts. Okay, that's infinite or it's very high. That's the way to state that. And you can see that over here, the current is 0, so the resistance must be infinite or very high. Calculate the resistance of the component when the potential difference is 0.7 volts plus 0.7 volts. You go up from plus 0.7. You can see that's at about 0.4 or 0.41. That's the current that you've got there. So they have a range of 0.4 to 0.3 in the mark scheme. So when you whack that through, R equals V over I, you end up with 1.71 ohms as your resistance. Practical uses for this component. So practical uses of diode is to convert AC into DC electricity, or as I stated before, it only allows the current to flow in one direction. Okay, I know I put I over here in the exam. Get into the habit of writing currents rather than just putting I when you're writing in prose. Okay, 14a, a simple definition question that people often lose marks on because of the fact they don't include a couple of key points.
So the first thing it says, explain what is meant by the work function of a metal. So that's the minimum amount of energy required to release an electron from the surface of the metal. I've underlined minimum, energy and surface because they are the key terms you must include in order to get this mark. Okay, minimum amount of energy to release an electron from the surface of the metal. 14b. So it's asking about the observations of photoelectric effect and how they support particle theory. And they're only asking for one observation and explain how it supports particle theory. We know there are 5 or 6 observations of the photoelectric effect that support particle theory. So to help me explain this to you guys, I'm going to show you the mark scheme and go through each one by one. Okay, so here we have the mark scheme. So one of the first points that you could have discussed was increasing the intensity increases the number of electrons emitted per second, or the number of electrons emitted per second depends on the intensity. So linking the intensity to the number of electrons emitted would get you 1 mark. You know the relationship between a photon and an electron is a 1-to-1, so that would have got you the 2nd mark. And then discussing that intensity determines the number of photons is the 3rd mark. So that's one way in which particle theory is actually explained using this idea. Okay, so you can only get those 3 marks together. You can't get one of these 3 marks and then one of the next ones. You can only get these in chunks of 3s. So if you then discussed increased intensity does not increase the energy or the speed of the electrons, again you could still mention here the 1 photon releases 1 electron, in other words a 1-to-1 relationship. But this shows the idea of the energy doesn't increase the speed of the electrons. Sorry, the intensity does not increase the energy of the electrons, then the energy of the photon is determined by the frequency, okay, and not the intensity. So if you're talking about increased intensity does not increase the speed or the energy of the electrons, you need to link that to the fact that the energy of the photon is determined by the frequency and not intensity. So another point you could have discussed was below a certain frequency or the threshold frequency, no electrons are emitted, sorry, I've just got this off the screen, haven't I? Just realised that. So I'm over it. So below a certain frequency, no electrons are emitted, and above a certain wavelength, no electrons are emitted. So that sort of idea, threshold frequency. The energy of the photons increases with or depends on the frequency, or E equals HF, we get the 2nd mark there, and each photon needs a minimum amount of energy, in other words a work function amount of energy, to actually release an electron. Okay, so sorry if you missed part of the other one before because it went off screen, it's at the top over there. I'll pause the video if you need to. Okay, so next one underneath over here, shortest one for the boys in the room. Okay, so electron emission starts at once. Okay, so it's instantaneous. Okay, it is it's not a build-up, it's instantaneous release. Okay, so even for low intensity, so even if there's a low intensity, 1% intensity, okay, even then you still get electrons emitted. So remember the animation that I showed you, even when we had 1% intensity, we still had electrons being released as long as it's above the threshold. And again, that is related to the idea that 1 photon releases 1 electron, and wave theory would allow energy to build up, but we know that was not the case. It had to be above that frequency, and therefore it was emission starts at once. It was instant, so it wasn't a build-up and then a release. It was instantaneous release of electrons. Okay, so the final set of 3 is increasing the frequency of light increases the energy or speed of the electrons, or increasing the frequency increases the stopping potential. That's EV. That's something we've also discussed as well. So the energy of the photons is determined by the frequency, or equals HF. So that's another time that points come up. So it's a standard point. So that point there and the 1 photon to 1 electron are 2 of the standard points that are almost always there as qualifying points that allow you to explain what's going on. And the bit underneath tells us that 1 photon releases 1 electron, or wave theory would again allow the energy to build up. So similar points to before. Okay, so the next question here talks about the idea of some electrically heated gloves that provide extra warmth, and we've got a circuit here which shows how the gloves work. So we've got 2 cells, each have an EMF of 1.5 volts, but they also have an internal resistance. So these are the internal resistance of the cells, and it says we've got a heating element that also has a resistance of 3.6. So let's label that so we know that if they ask about a heating element at any point, we know they're talking about the 3.6 and not the 0.2s that are inside. So calculating the total resistance in the circuit, so that's all the resistance added together, they're all in series. Okay, so it's going to be 3.6 add 0.2 add 0.2. Okay, so that gives us a nice 4 ohms. Please make sure you put the unit in there, otherwise you lose one of the easiest marks on the paper. Right, calculate the current in the heating element. Okay, so we want I. Okay, that's what they're after. We have R from above of 4 ohms. Okay, we have the total voltage. Okay, so that's 3 volts. Okay, so we have the total voltage there. So let's look at the equation. Okay, that's got V, I, and R in it. Okay, and as we've used many times before, R is equal to V over I. Okay, they want I. Okay, so we need to rearrange R is equal to V over I, which leads us to V over R. Okay, so that's going to end up being 3 over 4, which ends up giving us 0.75 amps. So 0.75 amps. Okay, so not very neatly written there, but you've seen how I figured that out. Now they're asking for the power output, but the key part of this is from the heating element, not from anywhere else, just the heating element. So if they want it from the heating element, okay, you've got to think about the resistance of the heating element. The information we have is we know the current flowing through there. We don't know the voltage it's getting really. We know the voltage of the entire circuit, but we don't know the voltage that's getting. Okay, so we can use current because we know the current is the same everywhere inside the circuit. So we want to use one that has current and power and obviously resistance because we have the resistance of the heating element. Okay, so again going back to our equation list, going to electricity and going to power, okay, we can see P is equal to I squared R is the equation that we want. So P is equal to I squared R. Our I is 0.75 amps. Our R is 3.6 ohms. So there P is equal to I squared R, so we end up with 0.75 amps squared, or the value squared, not the amps, and multiply that by 3.6 ohms. Okay, so put that through our calculator. So that is 0.75 squared multiplied by 3.6. Okay, it just gives us 2.03 watts. Please again make sure you include the unit. You don't want to lose sloppy Tonkit marks on units. Right. So B over here is talking about the internal resistance, and it says that each cell gradually increases its internal resistances when it's actually in use. So we know, and we can state that underneath or on the side over here as you're sort of planning your answer, that R is going to increase the longer it's on for. It's not big R, it's little r, it's internal resistance. State and explain the effect this will have on the power output of the heating element. Okay, so again we're talking about the power output of the heating element. Okay, so the idea to sort of plan our answer is that if little r increases, big R increases, which means I must decrease because the resistance is decreased. So I'm saying big R is increased because the whole resistance of the circuit. So when I'm saying big R there, I'm talking about the resistance of the circuit is increased. So therefore I must go down, and if I is going down, then P must go down as well. Okay, so power must go down as well. So let's get this into words. So if internal resistance increases, the circuit resistance increases, reducing current, therefore, remember you can use that symbol in the exams, by P is equal to I squared R, power also decreases. Okay, you can approach it by the idea of lost volts as well. So if the internal resistance of these increases, the internal resistance of these two increases, then there's going to be more lost volts, which means less voltage over here, which by P equals IV means less power output from over here as well. Okay, so again, lost volts you can approach it by, but I find this way a bit easier to explain what's going on. Okay, so question 16 is about energy levels. So the first part shows a diagram to energy levels inside a particular atom. Okay, so remember we know that when it's ionized it goes to the top end of this, and the ground state is the minimum amount of energy that it can actually have, lowest energy state, and you've also got transitions that can take place here, emission down, absorption up. Right, so state what is meant by an energy level. So remember, it's a discrete amount of energy of an electron. Okay, discrete amount, I should say. Sorry, I made a mistake there. Amount of energy of an electron. So draw on the diagram 2 arrows to indicate the two different transitions that will result in emitted radiation of the same frequency. Remember, frequency is related to energy in terms of the expression E equals HF. Okay, so if they're going to have the same energy, they'll have the same frequency. So we're looking for two with the same energy, and you can see that over here, the two with the same energy are the ones that go from 0 to 32 and 32 to 64. Both, so 0 to 3.2 and 3.2 to 6.4. So that transition, both have the same amount of energy. Key thing to note is this isn't in electron volts. This is in times 10 to the minus 19 joules. So if there's any conversions to take place later on, be careful not to fall for the trap of this being electron volts, because it's not an electron volt. Okay. C. A gas consists of these atoms. A gas consisting of these atoms can emit line spectra. Explain how this happens. So remember, in line spectra, electrons must become excited. That's the idea of giving an electron energy. That's what we call that process, them becoming excited. Okay, so that's one mark. When they become excited, they move into these discrete energy levels. There's your second mark. And as the electrons fall back down through, so as they fall down through these energy levels, they then release energy of a specific frequency. So as electrons fall through the energy levels, they release energy of a specific frequency. So that's E equals HF. You can also tie that in with the fact the energy of the photon is going to be equal to the difference in energy. Okay, so the energy of this photon that we use for E equals HF is going to be equal to the difference in the energy. Okay. So one of these atoms, so question D, one of these atoms in the ground state absorbs 3.6 times 10 to the 19 joules of energy from a collision with an electron. Calculate the smallest frequency of radiation that the atom may subsequently emit. Okay, so with this we've got to have a look at and see what is the smallest transition that can take place in terms of energy levels. So if we look back at the diagram, the smallest difference is between 2.8 and 3.2. Sorry about that, I was just getting a phone call. So E equals HF, so the smallest amount of energy difference it can get is going to be the smallest energy transition that can take place. So it's saying from the ground state it absorbs 3.6 times 10 to the minus 19. So if we go back to our diagram, 3.6 times 10 to the minus 19 will take us up to minus 2.8. So now we're looking for the smallest transition it can make on the way down, so it's clearly between 2.8 and 3.2. So the smallest energy difference we can have is 0.4 times 10 to the minus 19. So that's going to be equal to HF. Well, we want F, so to figure out our F, we need to rearrange for F, so that's going to be 0.4 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34, remember, which is Planck's constant. So there we go, that's in joules. That's in joule seconds, remember. Okay, so that should give us a nice value for our frequency. Minus 19, sorry, divided by 6.63 times 10 to the minus 34, which gives us 6.03 times 10 to the 13 for our frequency. Okay, so that is the smallest frequency of radiation we can get. That must be the case because it's the smallest energy transition that could have actually taken place. Right. Next it says to calculate how much energy in electron volts would be required to ionize the atom from its ground state. Well, we know ionization means it needs to get to this zero energy point from its ground state. So that's 6.4 times 10 to the minus 19 joules it requires. Now to do that, to do that, it needs to absorb a photon. Of course, they want to know how much energy this would need in electron volts. So we've got it in joules, we want it into electron volts. So to get into electron volts, you need to divide by 1.6 times 10 to the minus 19, and that would therefore give us 6.4 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19, which equals 4. So that gives us 4 electron volts as our answer. Okay, so our next question is about tidying up a prep room, and a teacher discovers a tray of resistance wires that have lost their labels. She then asks students to carry out an experiment to determine the material that each wire is made of by measuring the resistivity of the wire. Okay, so they mentioned resistance and resistivity, so that's going to be one of the key areas of this question. Okay. Explain why the teacher asked the student to measure the resistivity and not the resistance of a wire. Now we've got to remember resistivity is a property of a material, while resistance is a property of a component or a wire. It's a bit like stiffness and Young's modulus from Unit 1 materials, where Young's modulus is the property of a material, while stiffness is the property of a specific sample that you have. So the idea is resistivity, or rho, is the property of a material, while resistance, or R, is the property of a wire. So remember, resistance depends upon the dimensions of an object, while resistivity does not. Okay, so underneath, for part B, there's a 9-mark question. So not often do you get a question like this. And if this question was to come up for you guys, I would be absolutely gutted if you didn't get 9 for this, because it's a core practical that's actually described in it, and because it's a practical that you did as your Unit 3. So you're asked to describe a method to determine accurately the resistivity of one of the metal wires. Your description should include a circuit diagram, the quantities you would measure, the graph you would plot, and how you would determine resistivity. Right, so this is very, very straightforward in terms of what they're actually after. So in terms of the circuit diagram, I'd use my space below over here to draw my circuit diagram, or you could do it up here, but in terms of the space that's left, why not use that? Just make it clear by drawing a line down that you are using that space there. So the circuit diagram, obviously you need some sort of power source. Remember to include an ammeter. You've got your test wire that you're putting in there, and you complete the circuit with that. And then you've got your voltmeter in there as well, and you need some form of ruler to measure the cross-sectional area. Also, not the cross-sectional area, sorry, the length of the wire. Also, you need something to measure the cross-sectional area, and that's where you've got something along the lines of a micrometer to do that. So make sure you label any non-standard circuit symbols like micrometer, like ruler. Okay. So next, so we've done the circuit diagram, done that, tick it off as you do it. Next thing, quantities you would measure. So, measured quantities. So to list these, you'd have length of wire, which you know you're going to vary. State the unit. Get into the habit of doing that. State the unit, length of wire, potential difference. Remember, try and use that phrase rather than voltage. And remember, that's measured in volts. Current, which is measured in amps, and you know you're going to calculate resistance. You don't need to measure that, but you are going to measure diameter is what we're going to measure, not cross-sectional area. Common mistake, like I was going to make. Remember, that's measured in meters. Okay, so this will be in the region of a certain number of micrometers. Okay, so it would probably be somewhere in the region of 1/10 of a millimeter is usually what our wires are measured in. 1/10 to 100. Right, so you've got your measured quantities. Then you're going to need to say what, so if we go back to over here, then you need to say what graph you're going to draw. Well, you need to plot the graph, as you're fully aware, of R against L. But first you need to actually figure out R. Sorry, I'll get that back on screen. First you actually need to get R. So some way to state that R is equal to V over I. Okay, you're expecting a straight line graph with the origin like that. And you know the gradient of that graph is going to give you rho over A. Now, if you don't remember that from your Unit 3, number one, why don't you? And number two, you can look back at your equation list and figure it out from there. So if you look at electricity and we go down to resistivity, you've got the equation for resistivity there. So in terms of the equation for resistivity, it's R is equal to rho L over A. So our Y is R, our X is L. So therefore our M must be rho over A. There is no plus C. There is no plus C in this situation. Okay, so gradient, or M, must be rho over A. So, to figure out our resistivity, how we determine resistivity, the final point, essentially you know you've got to take your resistivity, will be figured out by the gradient times by the cross-sectional area. Now in terms of 9 marks, okay, that is pretty much covered there. The only thing we haven't done is we haven't said how we got our cross-sectional area. So cross-sectional area, remember, is pi r squared, and you say your r as well. So remember, you're taking your diameter and dividing by 2 to figure out your r. Everything on there would get you the 9 marks very easily. You've clearly stated everything that you need to do to figure out the resistivity of a wire. Key points that people often forget when doing this question, or this style of question. Okay, you're stating that you're measuring these things, but how do you get from measuring these things to what you've got on your graph? How do you get from potential difference in current to R? Well, we've stated that there. How do you get from your gradient to resistivity? Well, we've stated it here and over here, of course. I've stated it over here, sorry, and over here, of course. But how do you get cross-sectional area from diameter? So we're saying that cross-sectional area is pi r squared, and r is equal to diameter divided by 2. So it's being thorough and making sure you're stating everything you need to do to make sure you get all 9 marks available. Okay, so next question is question 18. It's talking about crystals when subjected to mechanical stress. Produce a potential difference, and these things are called this effect is called a piezoelectric effect, and they only really work with very thin films. So you've got a photograph of one of these. It was a built-in phone charger and it was tested at a musical festival, and you can see the white rectangular film on the person over here, which is this piezoelectric film. So by considering how sound wave travels through the air, that's the first part of this question, explain how sound can cause the piezoelectric field to generate a potential difference, the second part of the question. So let's have a look and see what I've written here. So sound waves are longitudinal, okay, we're fully aware of that, it's one of the marks. The waves have areas of compression and rarefaction. So the wave areas of compression and rarefaction. That's your second mark there. Or you could say there are areas where things have high pressure and low pressure. So similar sort of idea. Compression and rarefaction are better words to use. That's your second mark. Third mark can come from saying these vibrations apply a force on this film, and the fourth mark comes from therefore saying that force causes a PD to be generated, or a potential difference to be generated. Okay, so simple idea, wave comes in, moving backwards and forwards in terms of oscillating to produce mechanical stress on this film, and that film, because it has a force applied on it, that force is causing the potential difference to be generated. It's a nice question to get. A lot of people will trip up on that because it's applied in a scenario, but it's simple ideas that you know about and a lot giving away in the question. So it says over here, explain, for part B, explain why the crystals used in the t-shirt need to be in the form of a large thin film. The reason why is because therefore then it's going to be flexible and it's going to be lightweight, and sound doesn't have much energy as well. Okay, sound doesn't have much energy, so it's flexible and lightweight, it's going to be easy to move. The large area is actually there to gather a large amount of sound as well. So the key terms in here are the fact it's large and it's thin. If it's thin, it's going to be flexible and lightweight, and it doesn't need much energy to move it, therefore sound is going to be able to move it. And if it has a large area, then that's there to gather a lot of sound. So split that up into the two parts that make it up, and answer each of the two parts. So look carefully for that on future questions. It has two parts in there, just like the one before it over here as well. The two parts of that question, the bit about sound wave traveling through the air and how they generate a potential difference. Make sure you answer both parts of the question. That's a common mistake that people make when they don't look through a question carefully, underline the key terms. When the T-shirt is used at a music festival, the sound levels are sufficient to generate 20 kilojoules. So straight away I've converted that into 20 times 10 to the 3 joules in 10 hours. So straight away we know that time should be in seconds, so you convert that into seconds. So it's 3,600 for that part of it, times 10, so it's 36,000. This is enough to charge one phone. Calculate the electrical power output. So we know power is energy over time. Another one of the equations that's not given to you. You need to know that power is energy over time. We know that from Unit 1. So energy is 20,000 joules, and the time is 36,000 seconds. Put one over the other, and you end up with 0.56 watts. Okay, that's our power output. So give one advantage and one disadvantage of the charger compared with a conventional charger. Many different advantages and disadvantages, but I've picked the main two that I feel are important here. I mean, there's ones like, oh, you can't wash it, or it doesn't produce a lot of energy, but the main two that I think are the fact that it has a long charge time for a disadvantage, and an advantage as a free energy source. Okay, so at any scientific point would have got the marks here. If you said something like, oh, it's good for the environment, that's really not scientific enough. You need to be using some form of scientific data. So the majority of you would have picked up this mark, as long as you're stating a pure science point like this. So it is down to examiner discretion, this mark. Okay, so question 19 is asking about vuvuzelas. If you don't remember vuvuzelas, they are making the annoying sound from the World Cup. I'm not going to sit here and make the sound of a vuvuzela. If you can't remember what they sound like, you genuinely must not have watched the 2010 World Cup in South Africa. So, they're talking about vuvuzelas as a musical instrument which work by making the air inside vibrate to produce standing waves. So nodes, antinodes, straight away pop into your head as soon as we say standing waves. We know that there's nodes and antinodes in standing waves. Explain how a standing wave is produced. Right, okay, so two main ways in which a standing wave can be produced. You've got to have two waves somehow. It's either a wave meeting its own reflection, or two waves travelling in opposite directions. Okay, so two waves travelling in opposite directions, or you could say a wave meets its own reflection. That's fine. And the idea is that a principle is applied, and that principle is a principle of superposition. Okay, these waves need to add up with each other. So that leads to areas of constructive or destructive interference, you could say. But remember, it's the principle of superposition. It's the quickest way of getting that mark. Nodes and antinodes are therefore produced. Bang, nice easy 3 marks. Straight at the park, nice and easy. Okay, next question has a picture of the inside of a vuvuzela. You should be thinking about harmonics. We've been through this a few times, harmonics and overtones. So the standing waves produced in here, you can see it's open ends. Okay, so you've got points of maximum amplitude here, antinode with a node in the middle. You can see already on here there's half a wavelength, so I've labelled that the length of this tube is half a wavelength, therefore the wavelength is 2 times the length of this tube. Calculate the frequency. Well, how nice have they been to list things for us in a nice list rather than put it in the question. So saying the length of the vuvuzela is 60 centimetres, note centimetres, not metres, so we need to do a conversion here. The speed of sound in air is 330 metres per second. That's already in the correct unit. So therefore the wavelength we know is 2 times the length, so the wavelength is 120 centimetres, convert into metres, 1.2 metres. Well, from our equation sheet, we know we've got frequency and speed there, sorry, wavelength and speed there, and we want frequency. From our equation sheet, the very first equation, speed equals frequency times wavelength. Okay, that's the equation we use. Rearrange frequency. So therefore we end up with 330 divided by 1.2, so that's 275 hertz. Okay, so make sure you include the units capital H, small z, or you do not get the mark. A very nice 3-mark question. It's 3 marks because you had to convert the unit, and also because of the fact you had to spot that this is only half the wavelength here. Okay, it's a nice question to get. A lot of people trip up on the half the wavelength. A lot of people trip up on not converting the unit on that question. Okay, so final double page spread. Okay, so from right to the end of this paper now. The first part of it has a graph. It's got different frequencies of vuvuzela, so you've got a continuous range of frequencies there that can be heard by humans. So these are all the annoying sounds that we heard. You can see they've got different amplitude. So as soon as I see amplitude, I always think volume or loudness or some idea like that, because it's going to be related to that. So they're saying that at the World Cup it made it difficult to hear the commentators because of the vuvuzelas. So the solution was to use a filter that removed some of the frequencies produced by the vuvuzelas. So as you read through this question, I can see it's a 3-mark question straight away. I can see it's a 3-mark question. So I want to know where my 3 marks are coming from. So it says suggest 2 frequencies, so I need to make sure I suggest 2. That would be best to remove, so that's probably 1 mark attached to that. The effect this would have, there's a 2nd mark, and the disadvantage of removing all the frequencies, 3rd mark. So you want to remove those with the highest amplitude. They have the biggest effect. So you want to remove F2 and F3. That should be the first thing you should do. So that would be 1 mark if you stated that. That would decrease the volume of the vuvuzelas if you did that. So that's the effect it would actually have. That's the 2nd mark. So now we're going to talk about a disadvantage of removing all frequencies. Well, if you removed all frequencies, you might have removed some of the sound of the commentator, and that's where that 3rd mark comes from. Okay, so it's tricky in a sense that if you got rid of all frequencies, some of those frequencies will be the voice of the commentator, and you don't want that happening. So you won't be able to hear the commentator because of this. So you can't remove all frequencies. Also, you could have said none of the vuvuzelas will be heard, and you really don't want to get rid of all of the sound of the vuvuzelas, because then you won't get the atmosphere in the stadium as a football supporter watching it at home. So you want some of the sound of the vuvuzelas to come through, so you don't want to remove all of the frequencies. Right. DI. So DI is talking about noise cancelling headphones, and they work by detecting the sound and producing the sound that is an antiphase to that, causing destructive interference. So we've got 2 words in there, antiphase and destructive interference, and the question is asking for us to explain them. So let's go with antiphase first. So that's when one phase is 180 degrees, pi radians, or half a wavelength out of phase with another wave. So you need to say one wave with another wave and the difference between the two, 180 degrees, pi radians, or lambda over 2. So that's for 1 mark. Destructive interference is when waves cancel out with each other. There's a 2nd mark. Straightforward definition for that one. So excuse me. Remember, for the 3rd mark, you've got to say something about the sense that will have the same frequency for this to happen, or you could say that the same amplitude for complete cancellation to take place. There's your 3rd mark. Okay, so one of those 2 for the 3rd mark. Final question, nice straightforward question to get, 1 mark. Explain why noise cancelling headphones could not be used to cancel out the sound of the vuvuzelas. So remember, all sound will be cancelled if you did that, so therefore you won't be able to hear anything at all. And also the amplitude was not a constant, so it was tricky to actually cancel out something like the vuvuzelas, because of the fact that different vuvuzelas are different amplitudes, and therefore they will vary over time when people are blowing on in the vuvuzela harder, so it made a louder sound. So if it's not constant, it's difficult to noise cancel. So either of those 2 would have got your 1 mark for that question. Okay, so that brings us to the end of this paper. Hope you managed to go through it with me, and I hope you actually may remember to pause the video as we're going through it. If you haven't, remember it is on YouTube. You can watch this yourself at home to go through the paper again. Please do it again, and you want to try the whole paper again. See if you can get somewhere in the region of 70 plus marks, because you've already been through it once with me. If you don't, you should do it again until you get to that point, and good luck for your exam, guys.